Let's look at an example of a problem with a YY connected three-phase circuit. If we have a balanced source with a balanced positive phase sequence, a line impedance of 0, and a balanced load. We're also given that the VAN is 200 angle 0 degrees. We have RMS voltages, and we have the impedance on the BN phase. We want to find all phase and line voltages and currents and calculate the total power dissipated in the load. Let's look at some key things that's being stated in this. We have a balanced three-phase source, so we can use our theory about balanced three-phase sources to get all of our phase voltages. And we also have a balanced load. Regardless of the fact that we have a balanced load, because we have a balanced three-phase source, we also have balanced phase voltages. We're also going to have balanced line voltages. We can find them just due to the source. The balanced load will help us when we're trying to find the line currents. It says to find all phase and line voltages. It says and currents. So we have to find, do we have phase currents and line currents? We have to ask. We also are given that we have a line impedance of 0, so we don't have to consider any impedance in the line itself. And then we have to calculate the total power dissipated in the load. So let's convert that then to our givens and finds. And again, we want to make sure we state our key givens. So we have that balanced source. We also were given that it's positive phase sequence. So we know then that VAN leads VBN, which leads VCN. We're given a balanced load. So we can draw our diagram then with our givens on there. Here's our given at VAN. Here's our given. We're given the impedance at BN. So we can label those givens. And then we state what we want to find in terms of the phasor voltages. Or phasor voltages, the capital bold font, and we're using our double script notation, where the first two are the other phase voltages. Here are our three line voltages. And then here are our currents. We have a line current IAA, and then we additionally have this phase current IAN. Finding those, it asks to find the total power. Total power is the average power, so that total power is the power absorbed in each of these three phases: AN, BN, and CN. So again, based on our givens, we can just use our theory that we have about phase voltages. It's positive phase sequence, so 0 degrees leads negative 120 degrees. By that 120, so BN is negative 120, CN is negative 240. We're going to use positive 120, liking to keep our angles between positive and negative 180. But you could also use a negative 240 degrees for your VCN voltage. So we can label those on our circuit diagram. Additionally, it was a balanced load. So our balanced load, then our VCN is also 100 angle 60 degrees, and our our AN 100 angle 60 degrees. So it's drawn as a resistor and an inductor. We know a positive phase angle of the impedance gives us a positive reactance, and a positive reactance is inductive. We don't need to find out what these resistors and inductances are exactly. For now, we'll just leave our impedance as it's stated, and we'll continue to try to find our line voltages. So our line voltages, given our phase voltages, we can find our line voltages. Remember, we said given any one phase voltage or any one line voltage in a balanced, when we have a balanced three-phase source, we can find the other 5. And the key here is, what do? We multiply our phase voltage by that square root of 3 angle 30 degrees phasor. So AB is equal to VAN times square root of 3 angle 30 degrees. BC is multiplied by VBN square root of 3 angle 30 degrees. So increasing the amplitude or the magnitude of the phasor by square root of 3, and we're shifting the phase by a positive 30 degrees. So we can write out our calculation, and then we get our final answer. And this we can just do, we don't have to go to a calculator to do this. This we can do in our head. We're given 200, we just 200 times square root of 3. This is rounded to 3 digits, to 346. So that I guess you can put in your calculator. We can use 3 or 4 digits here. I know typically we like to use 4. To keep it easy for the example, we're using the 3 digits. The angles themselves now, we have 30 degrees, -90, and +150 for our line voltages. So where for our phase voltages, we would say our phase voltage, VP, is equal to 200 V RMS, and that's just a magnitude. Now we have our line voltage, VL, is equal to 346 V RMS, where we're using the RMS subscript, even though we know in power RMS is a given, we're using that to make that clear. Line currents we can easily find with a single phase. Now we were given a circuit, we weren't given that there was a line wire between the two neutrals, but we can draw that in. We know if it's a balanced phase and a balanced load, there will be no current on this neutral wire. But what's nice about drawing it in here is we can take out this one single phase. So we'll just look at our AN phase, and we'll bring out this nice simple circuit. Now that circuit became quite easy to look at now compared to that 3-phase circuit. If there was an impedance in this wire, I'll draw it as being resistive. If there's just a resistance on this line AA, we could draw that in here, and that would just be in series with our load impedance. Again, if there was a resistance on the neutral wire, we would not consider that here because we don't really have any current on this neutral wire. This NN here is not really here. We've just drawn it in so that we have a complete circuit in order to analyze. So if we do have impedances on these two wires, we would have to consider this one. We'll call it RAA, but we would not consider our NN. So that's key. It's not going to be key to this problem because there weren't any impedances. So the other thing that we see is that our phase current is equal to our line current. So if we find IAA, we find IAN. So there's no point in finding both. That's always going to be true in a YY system, that the phase current's equal to the line current. You only have to find the line current. And again, since we have a balanced source and load, that our neutral current INN is equal to 0. So then we can easily find IAA. We just have a voltage source across an impedance. We can just do that ratio. No reason to convert our impedance to rectangular form to find out what the resistive component and reactive component is, because this is easy to do. 200 divided by 100 is 2. 0 minus 60 degrees is -60 degrees. And we have our phase current our line current for phase A, so for AA. If we have our line current for AA, we have a balanced load at a balanced source, so we can find it for IBB and ICC. So our IBB is going to be IAA times one angle -120 degrees, right? That's just a -120 degree phase shift. So we have the same line current. So we could say in this balanced source, we have an IL that's equal to 2 amp RMS. Then we just have to figure out what that phase relationship is. So now we found the phase voltage, line voltage, and line current, which is the same as a phase current in a YY system. We can do our check here and draw our phasor diagram, where our VAN was at if we go back and look at what we found, our VAN was at 0 degrees. So we can start with that just at 0 degrees. Our BN, -120 degrees, CN, -240. If we look at our AB, it's leading AN as opposed to, our BN is lagging. Our AB is leading AN by 30 degrees. Our VCA is leading CN by 30 degrees, and again our BC leading BN. So all our line voltages are leading our phase voltages by 30 degrees, and then we can draw in our line currents. Our line currents have this 60 degrees. Actually, our line current AA is lagging our phase voltage AN by this 60 degrees. So the question is, can we just automatically draw these in, or what do we need to know for the line currents? And I'll give you a moment to see if you can't answer that question and think about how do we know that's 60 degrees? If you recall, our impedance had an angle of 60 degrees. So that impedance angle of 60 degrees is what we have right here. So our current, it's positive, so our current is lagging. Just like in an inductive circuit, the current lags the voltage by 60 degrees. It's VAN that is across our load, right? That's our VAN, that's across the load. So our current's got a lag by that 60 degrees for that inductive load. So we can draw that all up on our phasor diagram. So what we haven't looked at yet was the power. So if we want, we can look at the power in just one phase because we have a balanced source and a balanced load. So our power equation, the magnitude of the voltage times the magnitude of the current times the cosine of the difference of the two angles. Well, the difference of the voltage, our theta V minus VI, that's the impedance angle in that VN phase. So that impedance angle was 60 degrees. So we end up with so what this ends up being is it's equal to our VP times our IL, right? And then that's our cosine, that's triple Z of theta Z. Because that's going to be true for every single phase. The phase voltage is the same, the line current's the same, and the phase, phase angle of our impedance is the same. So our total, because everything is balanced, PAN is equal to PBN is equal to PCN, and they're all equal to that 200. So our total is going to be 3 times that, or 600 watts. So then we can check what we've said is our instantaneous power should be the same as the average power in a balanced 3-phase system. So we can go back and check our instantaneous power. If our radiant frequency is 120 pi, then, and we're given a 200 volt RMS VAN, then the amplitude of this we have to multiply by square root of 2, right? So that's 200 square root of 2 cosine, and because this is no longer RMS values, these are just our voltages. In time domain, it doesn't really matter, but we're converting that to voltage. And similarly with our current, that's 2 square root of 2, and that was angle negative 60 degrees. So then our power in time domain is just the product of the current times the voltage, but we have these two cosines, so we have to use our law of cosines, or well, it's not really the law of cosines, but our trig rule, where the product of two cosines is the sum of the cosine of the difference of the angles is the cosine of the sum of the angles. The difference of the angles, we cancel out the omega t, so we just end up with our cosine of negative 60 degrees, and then the sum of the angles, we get our 240 pi t, that's twice the frequency, minus 60 degrees. So if we look at our B phase, if we go and do the sum of these two angles, now we have 120 pi. Instead of the 0 degrees, we have minus 120. Instead of negative 60, we have minus 180 for our voltage and our current. But if we take the difference of the angles, we now have negative 120 minus 180. So we end up with the same cosine of negative 60 degrees. So we end up with that cosine of negative 60 degrees is still the negative, it's still the 200 watts. And then if we go to sum the angles, we end up with 240t. The sum of these two angles is negative 300. If we then look at our C phase, we still have the 200 watts there. These are all our average powers. And our 3 average powers sum to the 600. The power which is changing with time, they're all 120 degrees out of phase. So when we sum those, just like with our phasors, that goes to 0 watts. All right, so that's one example. We'll do some more examples of 3-phase systems.